We're live, perfect. So good morning, everyone. We will just wait 1 or 2 more minutes, just in case some people are a bit late.
Yeah, I think almost everyone is in, so you can take it from here, Vincent.
Okay, let's maybe wait. Let's give it 1 more minute.
All right.
I'm hoping to go over 30.
Ah, you're waiting for this, okay.
Okay, so just before starting, there is a chat box you can access on the right panel. So just feel free to ask any questions here. We'll have several sessions to answer those questions, but just feel free to write them down anytime. Hi, Joe. Good to see familiar names. Okay, let's go. So good morning, everyone. Good afternoon for the East Coaster. I'm Vincent Renaud, Sales Application at Axiom Optics, and here is Jeroen Kool from Confocal directly from the Netherlands. So this is a second session of the Re-scan Confocal Microscope webinar in the US. During the first one, we focused on the MicroManager interface and more precisely on the on-the-fly deconvolution tool from Microevolution. Today, we're gonna focus on a different add-on and different software interface. We're going to show the simultaneous multicolor confocal capability of the Re-scan Confocal Microscope. And this is going to be shown through NIS elements, so Nikon software. So here's today's webinar outline. I'm going to start with a very quick introduction of Axiom Optics, and then I'm going to give the hand to Jeroen, who is going to present confocal.nl and then to explain how does the Re-scan confocal microscope work, and especially what is the trick behind the resolution and enhancements. Then we're gonna jump to the demo session. It's actually going to be inverted. So we're going to start with a super resolution confocal capability. We're going to use the deconvolution tool from NIS Elements to show 120 nanometers lateral resolution. And then we're going to show the simultaneous multicolor capability of the system. 2 demo sessions because we're going to use 2 different samples. One is better to show high resolution and the other one is better to show, well, has several labeling, so better for multicolor capability. We're going to have a short answer session before each demo and also at the end. So again, feel free to ask questions whenever you want, and we'll answer them when it's time. So about Axiom Optics, we are a distributor. We are located in the US and we cover US and Canada. We specialize in optical instrumentation, and so not only microscopy, but this is the microscopy team. So Philippe and Neche on the East Coast and myself on the West Coast. At Axiom Optics, we in microscopy, we offer several add-ons. The Re-scan Confocal Microscope that we're going to present today, but we also have an add-on for single molecule localization microscopy and single particle tracking applications using adaptive optics to increase the localization accuracy. We also have a camera-based system for film and fret applications. Since it's camera-based, it can be used for any camera-based techniques, wide field, spinning disk, light sheet microscopy, and turf. And then we also offer the SensoCell optical tweezers and force measurement platform from Impedex, which is again an add-on for Nikon scope. This is for the microscopy systems, but we also offer cameras that are specialized for microscopy and for low light applications. We have wide range of cameras, different range of pricing and specs, of course. So the CMOS camera from Tuxen, which are very sensitive and very affordable must-go camera for any regular wide field, any regular fluorescence applications. For more high-end applications, we also offer the Hamamatsu SCMOS cameras. And when more sensitivity and faster acquisition is required, we also offer the iCam Trio camera from Lambert Instrument, which is an intensified CMOS camera. And then we also have the quality control solutions from Argolite, which are must-have for any microscopy facility. With that said, I'm going to give the hand to Jeroen, who is going to present you the Re-scan Confocal Microscope. So enjoy the webinar, and I'll talk to you for the answers session.
Thank you, Vincent, for the introduction. I'm going to take it from here. So let me start my presentation. Yep, there we are. So today we're going to talk about simultaneous multicolor super resolution imaging with the Re-scan Confocal Microscope. And this will be a theoretical session first, and after that I will do the live demonstration of this. So my name is Jeroen Kolen. I'm a product application specialist at Confocal.nl. And what I'll be showing you today is first the introduction to the RCM technology, some comparisons with other imaging modalities, such as wide field and other confocal systems. Then I'm going to show simultaneous multicolor super resolution imaging with the Cairn multi-split VieW, and some live cell imaging examples with this tool. And then finally, some configurations of several RCM setups, so different microscopes, different lasers. And after that, I'll move on to the live demonstration of the RCM in NIS elements. Okay, so a bit about Confocal.nl. So at Confocal.nl, we built the RCM, which is the Re-scan Confocal Microscope. This device can be added to any inverted or upright wide field microscope system, and it improves the lateral resolution of the system, and it turns it into a confocal system. So by purchasing this unit, you will save budget and end up with a better result. So it's a very effective tool to achieve confocal imaging. So you can upgrade your microscope. That's the main message. So this is a bit about what you can do with the RCM. I will show this movie later on as well. So here you see mitochondria being imaged for a very long time. And here you see the raw and the Huygens deconvolved data side by side. So this really nicely shows the resolution and the sensitivity of the system. More on this later. So let me go through. Okay, so a bit about how the RCM works. So in order to understand this, you first have to know a bit about confocal microscopy. So how does the confocal microscope work? In a confocal microscope, if you schematically draw it, you have the laser coming in, and then there's a dichroic mirror. Then you find a scanning set that scans the laser light towards the sample and is focused by the objective. So the laser light is focused on the sample by the objective, and then the emission light, the red lines here, can be traced back. These are descanned by the mirror and then focused on the pinhole, which takes care of the optical sectioning. And then finally, you detect the signal with a PMT. Now, what's a downside of using a PMT, a photomultiplier tube, is that they are relatively insensitive. So here, this is schematically drawn. So you can see we have the gallium arsenic PMT, which has quite a broad range of which is which is quite sensitive, but it achieves only 20% quantum efficiency. So only 1 in every 5 photons that ever reach your detector will be converted into signal. Then you have the gallium arsenic phosphorus PMTs, which are also called the gas PMTs, and they are a bit more sensitive. You find about 45% quantum efficiency there. But still, it cannot match to the silicon photodiode, which is the camera, the CMOS camera or CCD camera. And you can see that this one extends over a very broad range. So it's not only sensitive in the visible region, but also sensitive in the far red and in the near infrared. Okay, so at confocal.nl, we thought, why don't we make a confocal microscope which uses a camera as detector? So this is what we did. Actually, this is what Julia De Luca did in 2013. So you can see the original reference here down in the page. So what she did is she built a confocal microscope which uses a camera as detector. And in order to get the light onto the camera, a second pair of scanning mirrors was employed called the Re-scanning mirrors. And they are synchronized with the scanning mirrors up here. And they physically paint the emission light on the camera chip, if you like. So in this way, we can use a much more sensitive detection mechanism. Apart from the fact that we're more sensitive, we also improve the resolution of the system in the following way. So let me explain you just by some schematics. So here we see scanner and rescanner. So the scanner on the left side is scanning the laser across the surface, and on the right side you can see the emission light being painted on the camera chip. And if scanner and rescanner have the same amplitude, the resolution is diffraction limited, so nothing really special happens. You just have a diffraction limited spot on your camera. But we can play with the angular amplitude of the rescanner. So here you see that the rescanner does a double sweep, and initially this causes the spot to move faster, and therefore there is some motion blur that needs to be added. But if you scale back this image, and this is done by optics, so just by using lenses in the system, we can see that the resolution is improved. So we can have a 40% better resolution just by playing with this sweep of the rescanner. And if you would like to know more about this, there's a nice movie on our webpage, confocal.nl/explanation, which tells you all about this. Okay, some of our specifications. So our system achieves 170 nanometer lateral resolution at 488. And if you deconvolve the image, the resolution will be improved to 120 nanometers. The axial resolution, so the Z resolution, is similar to a confocal microscope, about 500 nanometers, and about 350 if you deconvolve. The quantum efficiency is camera dependent. So the nice thing about our system is that you can choose which camera you want. And it's anywhere between 80 and 95%. Then we have the scan speed, which is about 1 frame per second at 512 by 512. And if you decide to crop the field of view very much, then you can also improve the speed and therefore go up to about 50 frames per second. We use 4 lasers for excitation, so we can use 405, 488, 561, and 640. But we can also adapt to other wavelengths if necessary. And the pinhole inside our microscope is fixed, so there's no need to change the pinhole. This is optimized for high NA and high magnification objectives. So this makes this technique extremely easy to use. So with very little training, a user can get a very nice image out. And these images I will be showing more and more in the upcoming slides. So if you compare us to other modalities or other imaging modalities, you can see that compared to a wide field where the image is quite blurry, we are much sharper and have more contrast. And if you compare us to confocal, you can still see there is some fine resolution improvement. And this is caused by the double sweep. So here you see the 40% resolution improvement just by doing this extra sweep. And then we can see that if we deconvolve the data set, that the resolution is even further improved. So this 170 nanometer resolution can also be achieved with a normal confocal microscope. So some of you may know this. If you close the pinhole of the confocal microscope, you will be able to achieve 170 nanometers as well. But this is at the cost of your emission light reaching the detector. So only 95% of the light will then be blocked by the small pinhole. So only 5% will reach your detector. And you need a very bright sample in order to get the resolution improvement then. In RCM, because we use the double sweep technique, we are not depending on the pinhole. So here you can see that the raw images of the confocal 0.3 and the RCM are not comparable to each other. You can see that the RCM has much more contrast, and this is because we have an open pinhole architecture, and therefore a lot more light will reach your detector. If you deconvolve the data, it becomes even more pronounced that the resolution and the contrast in the RCM image are much better than in the confocal case. So sensitivity matters. That's the main point. So here is another very nice movie which we recently made. This shows mitochondria being imaged for 61 hours with one frame every 10 seconds. So in total, we acquired about 22,000 frames. And I want you to see that there's absolutely no bleaching here. The cells are completely happy. Some of them even go into mitosis. So you will see this in a bit. So here you see one going into mitosis, which means they're completely fine with the laser light that we put on these cells. Actually, we measured the laser light and it turned out only to be 1 microwatt of energy. So this is very, very low laser light, and still you can see that the contrast is quite high. Okay, so I told you 1 microwatt. So, okay, how do you measure this? So this is how we do it. We put a photometer at the sample plane, so at the objective, and then we measure the light. So here you can see 1 microwatt coming out of the objective. So very, very low laser light. This movie I also showed in the beginning of my presentation, but now I want to spend a bit more time on it. It's basically the same data set, but then deconvolved. So here you see raw RCM and deconvolution side by side. So you can see the improvement in contrast and resolution. And remember that this image is still 61 hours, so you can always do deconvolution afterwards. This doesn't put any constraints on the sample preparation. Okay, so 120 nanometers after deconvolution, this is what we can show. Then, of course, you can also do multiple color acquisition. So here you see cells being stained for ER in blue, and then there is mitochondria in green. And in red, we can see the nucleus, which is SIR DNA. So this probe emits in the far red. And remember that PMTs are not sensitive in this region. So cameras are, and this makes that this image has much higher contrast. So today it's about the simultaneous acquisition of multiple colors as well. So this is what I will be showing today, the Cairn Multisplit V2. So what is this device? This device physically splits the camera into 4 regions, and this is how it looks like. So you can see that this is a 3-color staining. So we see some DAPI, some GFP, and some red dye. And you can see that these dyes end up in different parts of the camera chip. So by using filters, we can make this happen, and this means that you can do 4 colors at the same time. So you have very little. You have no delay in between the color acquisitions, which is nice. And here you see then the composite image. So the software can automatically merge these 4 fields and make a 4-color image out of this. So this means that you can do 4 colors in about 2 seconds. And then 170 nanometers you find in the raw image, and 120 nanometers after deconvolution. So this application is also very useful if you want to do ratiometric imaging in, for example, calcium, or you want to do fluorescence resonance energy transfer, FRET. So then this is also very useful to use. Also, because there is no delay between the channels, it's very good for live cell imaging. So you have no mismatch between your colors. So here is a very nice movie that we made very recently as well. So these are mouse hippocampal neurons, and they're stained for mitochondria in green. In magenta, you find the nucleus. And in red, this is a self-filling dye which stains the neuron specifically. And watch all the dynamics that are going on here. So you can see all these mitochondria being moved around. You can see some transport here. So the movie will highlight it right here. So here you can see these blobs moving towards the nucleus. So retrograde transport. And we can observe mitochondrial trafficking away from the nucleus. So this is what you can see here. And of course, because the contrast is high, it's also easy to analyze these movies. It's not only to make nice movies, but also you want to have some data out of this. So here you can see some mitochondrial fission going on. And I want to emphasize that this movie was also made with the multi-split. So multiple colors at the same time. And many frames as well. Okay, so this was done with an Olympus IX83 and 40x 1.4 and a X-line objective. So because our system is camera based, you can also utilize the camera in wide field mode, which is nice because some people don't use the confocal or don't need the confocal. So they want to use the camera at the highest speed possible, and then you can go into the wide field mode. So simply by switching a lever called the bypass knob, you can switch between wide field and high resolution RCM. We are very flexible in terms of configuration, so we fit to the big four: Olympus, Zeiss, Leica, Nikon, but also other microscopes. You just need the one XC mount, so this is very standard. Then cameras, we can also utilize many different cameras, and we can utilize different laser sources. So very flexible. In terms of software, we have integration in NIS Elements, which is what I'm about to show. We have integration in Micromanager, which is a free of charge microscopy platform tool, which allows you to control any type of microscope. So any brand will work with Micromanager. And we made a driver for this, which is also freely available. Then very soon, actually next week, we're going to announce it today that there will be a Velocity webinar. Velocity is basically the commercialized version of Micromanager. So in Velocity, you're also able to control many different brands of microscopes, but then in a commercialized environment, so it looks more polished. Then image processing, I've mentioned several times SVI Huygens, so we have a dedicated RCM plugin for that. And more recently, we also started a collaboration with Microvolution. Microvolution is on-the-fly deconvolution, which can take place in Micromanager, but also in Velocity. So they have integration in multiple software platforms. And coming Thursday, we also have a webinar on this. So many webinars coming up. Now I'm going to show you some setups, so some customer setups. These are so this is a Leica DMI8 microscope. So on the left port we mounted the RCM with a PCO camera, and then here we can see a system at Johns Hopkins University in Baltimore, which is a Zeiss Axiom observer. And to the left port we find the RCM. We've attached to that the Hamamatsu camera, Flash 4. Then here's a very nice system at ETH Zurich, so in Switzerland, where they have a Nikon TI2 with the RCM mounted to the left port. And on the right port they have a 3D adaptive optics module, which is utilized for making 3D storm images. So what they do is they correlate the storm data coming out of the right port with the confocal data on the left. Very nice system. And then we have the setup which I used to image this this neuron. So here you can see an Olympus IX83 with cool LED as wide field illumination system. And then to the left of that you find the RCM attached to the multi-split. and a Hamamatsu Flash 4 detector. On top of that, there is a stage stop incubation system from Tokai HIT, and below that we find the Toptica 4-channel laser combiner. So today I'm going to show you a similar platform. I have one of my last slides shows the platform I'm going to use today for the acquisition. So I mentioned in the beginning, we also fit to upright microscopes. So here you can see the RCM being raised to the level of the C-mount by some legs, and then we can fix this to an optical table, and this makes the RCM also suitable for upright microscope systems. We also have another product. I haven't mentioned any of this in my talk yet, so this is new. This is the RCM near infrared, NIR, and this uses 640 and 785 excitation wavelengths. And with these wavelengths, you can penetrate much deeper into tissues and living specimens. Because we use the camera as detector, we also have the option to support cameras which have up to 60 or even 70% quantum efficiency in the near infrared. So this is very nice. And here we see an example of the near infrared RCM. So this was some autofluorescence captured at 785 at 20x and 100x magnification. So this really nicely shows the level of detail you can observe. And of course, because we have this double sweep going on, we also improve the resolution at these higher wavelengths. So the resolution at 785 excitation is about 240 nanometers, which is 40% better than what you would get with other confocal systems in this wavelength. Okay, so today's sample will be some mouse spermatocytes. So this is a nice sample to demonstrate the resolution improvement of the RCM. And as I mentioned, I'm going to image this with the multisplit, so we can do multiple colors at the same time, and then perform deconvolution inside NIS elements. So these are stained for SYCB3, which is a component of the synaptonemo complex, and it's stained with Alexa 488. There are also other colors. I don't know specifically the protein stained, but maybe you know better. And this sample was given to us by Anna Agostinho from the Sci-Fi Lab in Sweden. So this will be the setup I will use today, which is a Nikon TI-E microscope. It's about 10 years old actually, so it's a very old microscope, but still a nice platform to demonstrate the RCM. I'm going to use a 100x Plan Apo 1.45 NA objective and the Hamamatsu Flash 4 as camera attached to the multi-split V2 with the Toptica CLE as excitation unit. And as you can see, this is all mounted on a regular table, so our system is quite insensitive to vibrations. So this is nice. You don't necessarily need an optical table for our system. So just to summarize, the RCM is very sensitive, up to 4 times as sensitive as PMT-based confocal solutions. It's optics-only super resolution, but very easy to use, much more easy to use than for example, SIM, which is in the same order of resolution. And it's also a very affordable solution. So you can find on the webpage much more information about us, or contact our distributor, Axiom Optics in the US. If you're living outside the US, then you can find on this page listed below who is the distributor in your country. So that brings me to the end of my presentation. I guess there will be some questions. So Vincent, could you go ahead and answer already some of them? Then I'll make sure that the system is working.
Yes, I'll be happy to take over here for a few minutes. Will, about your question, actually, I think I need help from you, so we're gonna check that after.
Oh, you can do it now.
So the question was about the do we need a true global shutter readout for the camera for when using the multi-split? I don't think it would make any difference using or not using the multi-split.
No, so our system utilizes either a global or rolling shutter. So we send a TTL pulse to the camera. The camera opens and stays open as long as the TTL pulse is high, and then we write the information point by point, line by line, and frame by frame.
But so we'll basically the adding the multi-split will not change anything for that. So basically, when we use a CMOS camera, it's not a true global shutter, so I don't think it makes any issue. Then about the max speed we can achieve. So for the full frame with a multi-split, about 1K by 1K for color, it takes about 2 seconds. Then if you reduce the field of view in one direction, you can increase the speed. So I think we can go up to with a smaller field of view, about something like 50 lines. I think we can go up to 20 frames per second, something like that. Then the next question was about the field of view. Does the field of view is the field of view only 1/4 of conventional imaging, since it's divided the camera chip into 4 for the multicolor acquisition? So yes, correct. We're splitting the camera into 4. So if we use a 2K by 2K, we basically have a 1K by 1K 4-color image. Beside that, it's the calculations are what you would do regularly on a microscope. So it will give you 43 microns at 100x. Yes, one thing to mention is the Re-scan actually decreased by increasing the resolution. It decreased the field of view by factor 1.5.
Yeah.
So yes, so 43 micron with a 100x, 220 micron with a 20x. These are numbers to keep in mind.
Yeah, and if you so indeed the multi-split will cut the camera for individual regions, right? If you take out the multi-split, you have the entire field of view, of course. And Cairn also has the multi-cam approach. So if you have a little bit more money, then you can add 4 cameras, and they can pick up different parts of the spectrum. And this will also work with RCM. So then you have the entire field of view, but it's a bit more expensive solution, of course, because you have to utilize 4 cameras instead of 1. So yeah.
Okay, if you are ready, we will answer the next question after.
Yeah, sure. So if you have more questions, just feel free to drop them in the text. So I will turn on my screen share and then start sharing the NIS element screen. So here you can see NIS elements. So this is the Nikon software. And well, let me go over some of these buttons here. So in the upper panel, you find the OC panel, which is optical configuration. And here you can change the filter, basically. So you can go for bypass imaging, which means wide field on the camera, or you can do RCM. And you can do sequential acquisition of different colors, but you can also do simultaneous acquisition. And this is what we're going to do today. So we're going to do 4 colors at the same time. So let me go back to the bypass GFP. So now this will allow me to focus on the sample in wide field mode. So here you can see 1/4 of the camera being exposed now because of the multi-split. And here you can see the sample coming in focus. I will take a snapshot in order not to bleach it. So here you see these chromosomes. And as you have seen in my presentation already, these show a certain spread. So there's some distance between the chromosomes. But in wide field microscope, we cannot observe this. The resolution is not good enough. So we need to go to confocal microscopy. So this is where I'm going to click on RCM 4 colors. And I need to switch the bypass knob now. So this is a manual knob. Then, well, we do 4 colors. So I'm selecting all the lasers and I'm going to image at 1024 pixels, which is the maximum field of view in the multi-split mode. And then what I can do is I can change some parameters such as laser power. But these are also the only parameters that you have to change. So it's very easy to use. And then I can simply click on snap image, so capture. And now it's scanning with 4 lasers, and 2 seconds later you have your super resolved image already. And I hope you can see that here there's the chromosome is sort of spiraling around itself, and this you were not able to observe in the wide field mode. So there the resolution was not good enough. So here, because of this double sweep effect, we can improve the resolution and we can resolve this structure. So let me take this one step further. Let me make a Z-stack. So I'm now going to do 1.2 micrometers and 100 nanometers step. So that brings me to 13 slices. And I run this, and this is going to take about, well, you can see the time here. It's going to take a few seconds, about 20 or so. So here you can see now the data coming in. I will change the lookup table later because now it's a bit, the blue seems to be a bit oversaturated, which is not the case. But if I have this data set, then I'm going to deconvolve this. So this file is now saved. I'll also share this data with you later. So let me go ahead and deconvolve this data set. So first let's zoom in a bit and scroll through the Z-stack. You can see that here we are able to observe the spread between the chromosomes. Here they're too close together, so perhaps with some deconvolution we can still resolve that structure. So let's perform 3D deconvolution. And as you can see here, it already knows that the RCM is the imaging modality. It knows the objective magnification, numerical aperture. All these things are taken from the file. Only thing I have to do is fill in what are the emission and excitation wavelengths. So I know that this is 640 and this is about 660 emission. And we have blue channel, which is 405. And this one is 440. And this one is 488. And this one is around 500. Okay, and then I can deconvolve this. This will take a few seconds. And I want you to realize that this system is quite fast now. With every 2 seconds, we can take 4 channels at the same time, and then run through a Z-stack, or we can do tiling. So that's what I'm going to show in the next demo with the next sample. And here we have the deconvolved result. So obviously, as you can see, now I suddenly start to resolve a lot more. So here I can see that the spread is very pronounced, and here as well, you can see with some imagination that this chromosome is also spiraling. So let me go back one more time to the bypass just to show you that what we see is real. So here is the spiraling chromosome, and here you cannot observe it because the resolution is not good enough. Here we can. Oops. Where's my window? Do you want to save? Yes. No. Oh, okay. This is the deconvolved file. Sorry, it was complaining about the. Okay, all channels. Yes. So 4 channels at the same time, and you get around 120 nanometer resolution. So what I can do next is put the next sample. Perhaps Vincent, do you have some questions to answer in the meantime? Then while I put the sample.
Yes, we had few questions. So again, if you have more, feel free to write them down, and we will answer when we can. But we already have few here. So from Chanru, is SVI Huygens included? So yes, it can be included. It cannot if you want a package which is more cost effective, but you can if you want deconvolution with SVI. For deconvolution, by the way, there are several options. SVI is one, microvolution is another one. and NIS Elements also offers its own deconvolution package. The next question from Chehan was if we recommend SCMOS or EMCCD, what would be the difference in terms of specs? We recommend SCMOS. The main reason is they have smaller pixels, and that will give you a good sampling on the PSF, especially after the resolution enhancements thanks to the Re-scan technology. So yeah, 6.5 at 100x will give you perfect sampling at 60x as well. If you use bigger pixel, you will undersample your PSF and therefore limit your resolution because of the camera. That said, if you can trigger them, and most of the EMCCD on the market you can still use it. Just be aware of this limitation. The following question from Steve, hi Steve, was if the field of view, if the maximum field of view is reduced by a factor 4, so yes, as we mentioned it, the maximum field of view you can acquire will then be reduced by a factor 4 with the multi-split. So instead of 2K by 2K, you will get 1K by 1K maximum. The second question was from Andrew Allen about the large format cameras, 25mm or 32mm. We cannot do that. We are limited to the 18mm diagonal cameras, mostly because of the scanners limitation. And then the last question I had was from Boju. Can we get more than square root of 2 resolution enhancements? And sadly, no. It would be beautiful, but sadly, no. We are actually limited by the motion blur. So because we need to scan faster. I mean, the Re-scanners go they have a bigger amplitude, but the same frequency as a scanner. So basically, they go faster. Because they go faster, it introduces some motion blur. And so taking that into account, as well as the resolution enhancement, it's maximized. It's maximized with factor 2. If we go further away, if we go faster, sorry, the motion blur take over and then decrease the resolution. So square root of 2 raw data set is the best we can do.
Yeah, and that brings you then to 170 nanometers raw and 120 nanometers after deconvolution, which is, I would say, I always compare it with SIM and STAT. Of course, STAT can do more. With stimulated emission depletion, you can go to, yeah, they claim 30 nanometers if you have the perfect sample and the perfect objective. But of course, you need to put much more laser light on your cells. So if you ask your cells the question, which system would you choose, then I would think the cells will pick the one with the least amount of laser power. So the one that gives the highest resolution and the least amount of laser power. And I think we are pretty much there. So our system delivers good resolution, but on top of that, it's also very light effective.
Before starting again, I just want to mention the question from Bruno. I think we answered it already. So yeah, let us know if you didn't get the answer, and I'll be happy to get back to you. I think Jeroen, you're ready to go, right?
Yeah. So let me.
So we'll start answering again after this demo session.
Yeah. So let me take these maybe 2 or 3 minutes to image this last sample. So these are BPAE cells. They're stained with DAPI, so nuclei. You will find phalloidin. There is some mitochondria in red. So I'm going to focus on the sample now. Might take a bit of time because there we are. So
okay, so I'll take this opportunity. Do I have 1 or 2 more minutes to answer questions? Oh no, you're good already.
I'm good already.
Okay, well, we'll have to wait then.
Yeah. So here is the. So here are the cells, and what I just wanted to show you is now that this also works with stitching, for example. Okay, so what I can do now is I can I switch off the Z stack, and then I choose large field of view, let's do 4x4. Why not? And at this XY position. So I'll also save this data. PPAE stitched. Okay, so here we go. And then I can run this. And this is again going to give me, let me first see if the sample is still in focus. This is again going to give me 4 channels at the same time. I will slightly enhance the focus here. I was not completely happy with that. Here we go. This is more focused. Okay. And now we can run this. So this is just to illustrate you that this also works with whatever experiment you want to do, stitching, time lapses. The RCM serves as a camera, so it will do all these things. And this is then also going to compensate for the field of view, or for the lack of the field of view with the multisplit. Because if you have 4x4, effectively you will have 4,000 by 4,000 pixels. So you have a larger field of view. And this is not at the cost of speed, because we're doing all the images, all the channels at the same time. So here you can see these cells now stitched. You can see I slightly bleached the center. I was a bit slow in focusing, but anyway, I hope you're able to appreciate now that. Oops, where did my here it is. Yeah, where did my nuclei go? They're here. So as you can see as well, the dynamic range on the camera is huge. So it's impossible to oversaturate with this kind of system. I'm just playing now with the lookup table to make the image look more pretty. So in the yellow we have the mitochondria, and in blue, of course, the nuclei. So this looks better. And then we can zoom in and we can really see that the level of detail is maintained here. So we have nice detail in the sample. Okay, so this brings me to the end of the demonstration. I'm sure that there are some questions which we can answer still, so I'm happy to take them.
So the following questions was from Dechen about the actual resolution. I'm not sure we mentioned it. So yes, the lateral resolution raw data is 170 nanometers with a high NA objective. After the convolution, you go down to 120 nanometers. But the actual resolution, there is a slight enhancement, slight improvement of the resolution thanks to the Re-scan technique, but it's about 15%, so not much. So instead of 550 nanometers actual, we end up with 500 nanometers raw data. And after the convolution, we go down to 350 nanometers. So yes, slight improvement. About the chromatic shift, yes, I saw it as well. So when we looked at the chromosome in the deconvolved dataset, we were able to see some chromatic shift. I mean, was it the case, Jeroen? And if it is, does it come from the multisplit or from the objective? I don't know. Oh, Jeroen?
Yeah, sorry, I dropped out. I'm back.
It's okay. You're back. So we were discussing the chromatic shift we saw, you know, when imaging the chromosome.
Oh yeah. So this is it. This I can comment on. This is not caused by the lens or the RCM. This is a slight misalignment in the cubes of the multisplit. It's relatively easy to align, but it's quite hard to align it perfectly on the pixel. So maybe it's my experience that I haven't played around with it enough, but it's for surely that. So it's the shift that you saw from the green in the red channel. I also observed it. There was some chromatic shift is caused by the misalignment of the cubes inside the multisplit. But this can also be fixed later on. You can also take a reference image, and then you can shift your images with software compared to each other to get the perfect pixel alignment. I would say for these kind of applications with the multi-split, most interesting is to utilize it on like living cells, so on living specimens. You can image 4 channels at the same time, and then if there's 1 or 2 pixels shift between the different channels, I wouldn't say it's such a big problem. You can always counteract this with some software. Yeah. Or if you're really good at aligning the multi-split, then. Okay. So more questions?
We had a comment from Jez about using. I mean, actually, we could turn that into a question. You know, if we use a bigger camera chip, could we get a bigger field of view using the multi-split? We go, for instance.
No, so it's important to realize that the chip of the camera indeed determines the field of view, but as Vincent mentioned, that our system is made for 18 millimeters diagonal of the chip, so you can make the chip bigger, but then it will fall out of the reach of the RCM. And if you
if we use
more pixels.
Sorry, I'm cutting you because I think we're going in the wrong direction. If we use a bigger camera but with a multi-split, could we do, for instance, 2K by 2K, which is basically still 18 millimeters diagonal, but it will be spread into 4 different parts of the bigger camera chip.
Yeah. So
you see what I mean? Yeah.
If you go to you want to add more pixels, that's what you're saying, right? You want to have more pixels in the camera and therefore have a larger field of view, but this will only affect the sampling. So again, we now utilize an 18 millimeter diagonal camera, which is the max that the RCM can handle. It's the maximum field of view. And if you add a bigger chip, then these pixels will just be dark because they cannot be illuminated by either the multi-split or the RCM. So yeah.
Okay. So the answer is no, Jez.
Okay.
Any other questions?
Then I'm going to share one more thing. This is about Thursday. I was looking for this data. So on Thursday we have another webinar coming up on microflution. So let me quickly find this. Where is it? I'm finding this document. Anyway, it's on our webpage. So if you go to confocal.nl and you go to the Let's Talk About webinar series, you find there you find the registration page. I found here the document, so I can start sharing it with you guys. So it's here. So Mark Bruce is going to give a presentation on microflution, and I'm going to demonstrate microflution on the fly in Micromanager. So this is coming Thursday at 4 o'clock European time, which is 7 a.m. Pacific time and 10 a.m. East Coast time. Okay.
Perfect. I will follow up with everyone here with some polls actually to get feedback about this webinar, and I will also include some links for further information about the Re-scan technology, how it works, and things like that. And also maybe I'd just like to mention the price for such a system in USD. So confocal, like an add-on. Confocal add-on, including the RCM, a 4 laser line combiner, the camera, and the multi-split will be around 120,000 USD. Thank you so much for attending this. I hope it was interesting for everyone, and we hope to see you soon. We'll have more webinars to come.
Thank you very much. Bye-bye. Have a nice evening.
Thank you, bye.
Have a nice day.